Okay, these are the 2.2 part 1 notes, and we're going to be talking about density curves and normal distributions. Density curves are something that you're going to see fairly often in this class. It's something that you see fairly often in normal statistics. And the normal distributions is going to make up a fairly large part of this class. I can pretty much guarantee that you're going to see at least a couple multiple choice and maybe a free response. More than likely a free response, I can't guarantee it. But a question related to normal distributions, it's a really, really large part of the course. It's a really important concept to grasp. So it's important that you're paying attention, asking questions when you're unsure, and you have a solid grasp on everything that kind of falls under a normal curve or a normal distribution. So a density curve is a new way of representing the overall pattern of a distribution. The entirety of the curve must be above the x-axis, and the area of the curve under the curve must be equal to 1. And this area of 1 is representative of 100% of the observations falling within the boundary of the curve. So basically, you can make a density curve of anything, and what you're saying is every response that we recorded is included in this curve. The total area of the curve represents 100% of respondents. So if we were to make a percentile, when you do the entire curve from the left to the right, that curve is 100% of respondents. And then various points in that curve represent various percentiles of respondents. The median of the density curve is the equal areas point. So if we were to think about this, like let's say that, let me break it down in terms of just squares. If I had a long square like this, and then I had a square like this, and we said both of their areas were equal to x, that's equal areas. So in terms of a density curve, if we had a density curve that looked something like this, where it kind of had this weird square shape, and I'll do that in a different color. Let's say that we had a density curve that looked something like this. That means that the median is going to fall somewhere there, where those two areas are equal. And again, that's not perfect, but that's just letting you know. The mean is a little bit different. The mean is the balance point. So that's thinking of the median is purely the area, but let's say that we're talking about the density curve of salary. So we're thinking about LeBron James making so much more on the Lakers. So their density curve looked like that, where everything happened within the 1 to 3 millions, but then you have LeBron James making a ton. The mean falls somewhere different, where these areas are not equal. This area could be X and this area could be Y. But what we're saying is their density, or their weight, is about the same. We're saying that this is equal to Z amount equal to Z amount. And the book has a really good representation of it, of putting it on a scale, and that scale would balance out. So another great example would be, let's say that we had a bunch of we had a balloon versus a tennis ball. The balloon and the tennis ball, they might end up having the same amount of area, but that balloon and tennis ball could have a much different weight. So the median of the size of the balloon and tennis ball could be the same, but then you would have to cut off parts of the tennis ball to balance it on a scale to make it work out. So you can take some stuff out of the median. You can take values from the median to get your mean, if that kind of makes sense. But I really would look at the book. That example of having that scale, I think, is a really, really good visual of the mean versus the median. And again, we should kind of start understanding that now. One thing I thought was really good with that chapter 1 quiz was a lot of you were able to identify that the median is resistant to those large values where the mean is not. So that mean shifts because of those large values. So if we have those skews, we're going to see it shifting. And again, I've got 3 common density curves. We're about to learn about the normal curve, and then we've got 2 skewed curves. Your book has this as well. And we can see that on a normal curve, your mean, median, and mode all kind of lie at the exact same spot. They should. Again, it's not going to be perfect. When we say they all lie at the exact same spot, that's in the ideal normal curve. But we rarely see an ideal normal curve. But if you had something, if we had distribution of height, and we said the distribution of height, the median was 68.99 inches, and the mean was 69.12 inches, then we're going to say that they're basically the same. So that was probably going to represent a normal distribution. And then the mode, your book doesn't go into detail there, but obviously, like, your mode is going to occur at the peak. It's going to occur at the most common response. So we don't really deal much with mode in this class, but that is something that you could know just as kind of a side fact. Now we see with our skewed graphs, we'll start here with our right skewed graph. Make sure, one issue I saw, we had a little bit of confusion on the quiz with what is right versus left skewed. Again, we're thinking about skiing. This is a right skewed because it has that tail. It goes out on and on. This right skewed graph, the mode still occurs at the peak. So wherever you have your peak, wherever you have your highest point, you're still going to have your mode. The median is shifted a little bit to the right of the peak, but the mean is shifted really far to the right of the peak. Again, if we're thinking about equal areas versus like density or weight. So here, this would represent an area of X, just like to the left of the green would represent an area of X. Now, on the left side of the mean versus the right side of the mean, that's where it would balance out, where all the values together, all the observations added up, are equal to each other, added up and divided, finding that average. On a left skewed, we see that exact same pattern, but it just moves to the left of the median is pulled to the left along with that skew. The mean is pulled to the left along with that skew as well, because the mean isn't resistant to those large values, while the median is. So the median does get pulled because we do have values moving that way, but it doesn't get pulled nearly as much as the mean gets pulled to those directions. So I've got a brief check for understanding. First of all, explain why this is a legitimate density curve. That's this fact right here. The total area under the curve is 1. You need to have a total area of 1 under your curve for it to be a density curve, because that's representing 100%. About what proportion of observations lie between 7 and 8? Well, the area between 7 and 8 is 12, so that means about 12%. And I guess since we're talking about proportion here, we would say that 12 out of 100. About 12 out of 100 observations lie between 7 and 8. So if you had 300 observations, about 36 of them lie between 7 and 8. You could report that as a percentage, but they're asking for a proportion here. Here, mark the approximate location of the median. Again, we can see here that this is skewed a little bit to the left. So the median is going to occur just a little bit to the left of that peak. I'd say that it's going to roughly fall around there. And then again, the mean. So let me actually mark this as median because question 4 is looking for the mean. And that mean is going to fall a little bit more to the left than the median. And again, I'm just eyeballing this. If you had a question like this on the AP exam, it's not going to be looking for anything perfect. They're not going to be pulling out rulers and seeing if you got it exactly right. They're going to want to see that you know, okay, I'm looking at a left skewed density curve, so that means my median's going to move to the left and my mean is moving more to the left. The mean and median have this relationship because the median represents the area. The mean represents kind of the balance point of like the weights of the two sides. The mean gets pulled farther to the left because we have those extreme values on the left. The mean is less resistant. So you can see now where we're really pulling a lot of that information in from chapter 1. One thing I love about stats versus normal math is in my pre-calc class, you can kind of truncate chapters a little bit. Yes, a lot of things carry on, but in stats, we're going to still be using a lot of those same terms all throughout the year. So knowing that mean is affected by that left skew, knowing that it's pulled by those extreme values while the median is not. That's why they have this relationship, and they both move to the left, but the mean moves to the left more. All right, normal curves. They're an especially useful density curve with a number of applications. Normal does not mean that it occurs frequently. We don't call it a normal curve because it's the most common form of a distribution. In fact, it's kind of a relatively rare form of distribution. But when it does occur, there's a lot of information that we can get from the density curves. There's a lot of information that can be gathered from normal distributions. And there are a lot of things that have normal distributions. The book does a good job of presenting it, like error in measurement when we're talking about mass manufacturing, when we're talking about heights, when we're talking about IQs, when we're talking about test scores. A lot of things end up abiding by relationships and patterns that we see in normal distributions in these normal curves. So we take a lot of we take a lot of time to look at normal curves and see how we can approach them and what they mean. All normal curves are symmetric, they're unimodal, and then they're bell-shaped. And then the normal curve is described by giving its mean and the standard deviation. Now, the mean is located at the center of the symmetric curve. So you find the peak, it's right in the center, it's symmetric, and that's the mean. And it's going to be the exact same as the median. So going up here, we have that normal curve that we drew. And that normal curve, we can see the mean, median, and mode are all the same, and we would expect that as well. If you change the mean without changing the standard deviation, adding or subtracting, you just move it on the axis and it stays the exact same shape. So let's say that this were representative of some normal distribution. If I were to subtract the same number from every value, it would shift to the left. If I were to add some number to every single value, it would shift to the right, but that distribution would stay the exact same. The frequency would occur at the exact same level, and that's one of the things about normal curves. And then finally, the standard deviation controls the spread of a normal curve. The larger the standard deviation, the wider the curve gets. So if you have a standard deviation of like 0.2, it's going to be a very narrow versus a standard deviation of 10. And when you draw your curves, it's going to vary based on what your median value is, how high your curve goes, etc. But again, if you have a large standard deviation, that curve is going to expand. Now, how to read a normal curve. When we talk about the standard deviation determines its width, we have these ways of breaking down what a normal curve is. The book says that you can kind of eyeball where the standard deviation is. I think that's a little bit extreme. I understand where they're saying that you can eyeball the standard deviation to a certain extent. I don't think it's going to be perfect. I think that they make that sound a lot easier than it actually is. When you look at a normal curve, you kind of get used to what the separations are. Basically what you represent here is you can divide the normal curve into these sections. This blue section represents from the mean out. So this light blue section to this first line on the left represents the mean minus the standard deviation. To the next line is minus 2 times the standard deviation. Just like over here, to this line is the mean plus 1 standard deviation, the mean plus 2 standard deviations out to that next line. So when we make this curve where we start seeing it go down, eventually we draw our line for standard deviation. Well, where do those lines come in? That's a big question. And that's where the 65 or 68, 95, 99.7 rule comes in. And basically 68% of your data lies within 1 standard deviation of the mean. 95% of the observations lie within 2 standard deviations of the mean, and then 99.7% of observations lie within 3 standard deviations of the mean. I like the one that I have on the right here a lot better, where 34% of your observations lie 1 standard deviation to the right of your mean. Just like 34% of your observations lie 34% to the left of your mean. You've got 13.5% that lie between 1 and 2 standard deviations on both the left and right. When you add those, you get a total of 57.5% lies within 2 standard deviations to the... Nope, that is not the right math. That is 47.5%. 47.5% lies within 2 standard deviations to the right, just like 47.5% lies within 2 standard deviations to the left. And then we can even draw another level, and we could say that you've got 2.35% there. So we've got 49.85% to one side, and then we've got another 49.8% to the other side, 85% to the other side. And this is all based on your standard deviations as you go through. It's pretty straightforward there. It's a rule that you really should memorize. You should have this off the top of your head. Get used to it. We're going to be doing a lot of examples with it. All right, a couple notes. The 68, 95, 99.7 rule only applies to normal distributions. This is just a quick note in the book. I'm going to touch on it. There is the Chebyshev, I'm going to assume that's pronounced, inequality, which states that proportions of observations falling within a specific number k of standard deviations from the mean is at least 1 minus 1k over 2 over k squared. Like any distribution at all, if you were to say that you had 1 minus 1 over k squared, and like you said, okay, how far is it from one standard deviation? That's suggesting that at least 0% of your data is going to lie with, from within one standard deviation, etc. So just kind of breaking that down. But it's not a big deal. You do not really need to know that. All right, check for understanding. You've got a distribution of heights among young women aged 18 to 24. It's approximately normal. You've got a mean of 64.5, and you've got a standard deviation of 2.5. Sketch the normal density curve for a distribution of young women's heights. Label the points 1, 2, and 3 standard deviations from the mean. So I'll do that down here on the homework slide. Easiest way to do this is kind of draw your bell curve and then draw your x-axis. I am not an artist. I realize that is what every math teacher says always, but really I'm not. So this does not look great per se. I understand that. Let me at least make a better axis. So we've got our density curve here. Right in the middle is going to be our mean. And that mean is going to be 64.5. Then we're going to, the book says that you go until you can kind of see that the slope changes to make one standard deviation. So we're going to say that within one standard deviation, it moves out 2.5. So this value here, we've got 64.5 inches. So we add 2.5 to that, we got 67 inches. Over here, we subtract 2.5 from that, we got 62 inches. We'll move out a little bit further to get to our second standard deviation. Again, I'm kind of eyeballing this. I realize this is not perfect. We're just trying to make the point here. So over here, we'd have 59.5 inches. And over here, we'd have 69.5 inches because we're adding 2.5. We're moving out another standard deviation. And then finally, we'll move out another third standard deviation. So here, we add 2.5 to get to that next standard deviation. That would be 72 inches. And then over here, we would add another standard deviation. We're going to subtract another 2.5. So we will be at 57 inches. So that's our normal curve there with that standard deviation of 2.5 and that mean of 64.5. You first draw your mean, you move out one standard deviation, you subtract on the left, you add on the right. You move out another standard deviation, subtract on the left, add on the right, etc., etc. Again, they're not going to be perfect, but you can get that general shape. What percent of young women have heights greater than 67 inches? So that's where we're looking. All right, 67 inches occurs here. It's one standard deviation out from the mean. And this is where you have to start kind of thinking some. So what I'm going to say is represented here is 50% of the data. And then I know, because I have this normal distribution up here, to the left of the data, within one standard deviation, I've got another 34%. So I come down here and I say, all right, this distance is another 34%. I've got half the data on the left. So that means that 84% of women 18 to 24 have heights less than 67 inches. So I'm just going to do the reverse. I'm going to say that 16% of women have heights greater. Another way I could have looked at this is I could have said to myself, all right, I know from 67 onward, I know that at that standard deviation point, there's 13.5% and 2.35%. And then I also know that there's 0.15% to the right that's not accounted for. Beyond 3 standard deviations, there is 0.15% of data that falls beyond that 3 standard deviations. So I could go through and say, all right, 13.5 plus 2.35 plus that last 0.15% is equal to 16%. So 2 ways I could have approached that. What percent of young women have heights between 62 and 72 inches? So that's where I look here. 72 inches. This falls at the 99.7 because it's the 3rd standard deviation. So that means here between 72 and 64.5, I've got 49.7% of my data. Over here between 62 and 64.5, I've got 34% of my data yet again. So I'm going to add that 34% to the 49.7, and we will see that this is 83.7% of the data lies, or of the heights lie between 62 and 72 inches. So less than a foot, that's saying between 5'2" and 6 foot, 83.7% of young women aged 18 to 24 have heights in that. And that kind of makes sense to me based off what I see in the real world. And again, we can see that that's really, really close to number 2. Again, that's because we're including 1 standard deviation plus 1 side. In B, number 2, we did all of this to here. While in C, we did from here over here. The only difference is in number 2, we included past the 3rd standard deviation, while in number 3, we didn't include that 3rd standard deviation. I realize I didn't say much about the Chebyshev inequality, and it might not make sense. When I say that within 1 standard deviation, at least 0% of the data is there, I mean, that makes sense. So that's saying that as long as you have data, basically, like it should fall within 1 standard deviation, or maybe you do have data and it doesn't fall within 1 standard deviation, but like we consider a normal curve. 68% of our data falls in to the normal curve. That's at least 0. So we're saying that we at least have that much. If we're talking about, like, let's say 3 standard deviations, we're saying that at least 8/9 of your data will fall within 3 standard deviations. In a normal curve, 99.7% of your data falls within 3 standard deviations. So basically we're saying the more standard deviations you have, the more and more data that should fall within that standard deviation out from the mean. So it doesn't really matter how skewed you are. If you have standard deviations, we're going to move to a certain point, and this is going to get larger and larger. The more standard deviations you have, the more data which should be included within those standard deviations. So, again, reach out to me with any questions or concerns. There's a homework assignment. I think this homework assignment's pretty quick. There are some homework questions that you don't really get in the notes. The book doesn't really explain it. It doesn't explain a uniform distribution, but you should be able to take what you've learned here and apply it. So work on that homework. Reach out with any questions that you have, and have a great night.